lab is going to talk about some determination of alpha strong from hadronic events. Thank you.
All right. Thank you very much. Good morning. So yeah, I'm Chris Lee from Los Alamos, and I'd like to thank the organizers, especially Vicent, for the invitation to be here, which came about more than 2 years ago, I guess, and could not have predicted that the talk would happen on the 1st of October. And you really have to appreciate my dedication to be here today, because this happens to be my wife and my third wedding anniversary. So I'm really risking a lot to be here. So since I know this is on YouTube, I have to tell my wife, I love you. I'll be back home tomorrow, in 2 days. I'd like to also wish Professor Dominguez a happy 77th birthday, as you told us yesterday. And in Los Alamos, as I told you after coffee yesterday, we do now believe in multiplicative renormalization. Yeah, so we've moved on. So I'll tell you about determining the strong coupling from observables called event shapes in E plus E minus collisions to hadronic final states. When you were organizing this workshop, I thought there would be a few other talks on the topic. I didn't realize I might be the only one. So I'm not sure exactly, I wasn't sure exactly how to target this talk. Whether I think I'm also the first talk that may use soft collinear effective theory, which may show up tomorrow, so maybe I have to introduce that, to introduce other people's work on event shapes, and then show my own group's results on predicting a new class of event shapes and determining alpha S from that. So I thought, well, I have enough time to do one or two of these things well, or all of them poorly. So I chose to do all of them poorly. So let me rush. Let me acknowledge my collaborators on the predictions for the latest predictions for these event shapes called angularities, which I'll introduce at the next to next to leading log prime order matched to next to leading order fixed order predictions. I worked with Guido Bell at Ziegen, Jim Talbert, who was at DAISY and is now at Niels Bohr, and Andrew Hornig, who was my director's postdoctoral fellow at Los Alamos, who I have to acknowledge that really a lot of work in this field, and very tragically, at a young age, he passed away last year unexpectedly. So this work I always dedicate to his memory. I'll show you some preliminary results, if you want to call them that, from the ongoing with a couple of the same collaborators, and also with Yanis Makris, who was at LANL until recently and is now in Pavia, and Hugo Prager, who was at Ziegen and now is at some unknown location, either in the Himalayas or Iran, last we heard. He left, he's on an adventure. And I'll show you some results from that work that's in progress. So first, an introduction to event shapes. So these are nice observables which are very global measures of kind of jetty structure of events. I mean, hadronic jets are well known as probes of QCD, and also our figure in searches for beyond the standard model physics. But defining a jet requires algorithms, cut parameters, and all this. It can get messy. So event shapes are a really nice, simple way globally to measure if an event kind of looks 2-jet-like or 3-jet-like or whatever. These are 2-jet event shapes. The most well-known is the thrust, which is this sum over the projections of the 3 momenta of all the final state hadrons onto some axis, t, but where the sum is maximized over the choice of that axis. So for once you find that axis, the thrust, you can divide the event into 2 hemispheres, and the thrust ends up just being the total magnitude of the 3 momentum in 1 hemisphere normalized to q over 2. For an exactly back-to-back 2-jet event, this thrust is 1. We like to define tau as 1 minus capital T and call that the thrust, because that goes to 0 in the 2-jet limit. The maximum value of thrust is a half for a totally spherically symmetric final state. Another example of an event shape, which I won't talk about, just to illustrate a different way you can define it, is to also sum over the transverse momenta of particles relative to the thrust axis rather than the z momentum. And that also goes to 0 in the back-to-back 2-jet limit, but has different properties than the thrust. Another event shape that I'll show past results for is the so-called C parameter, related also to Fox-Wolfram moments. But it's basically the sum of products of eigenvalues of this tensor built out of the momenta of the final state particles, which can be written as this pairwise product of correlations between momenta in the final state and the pairwise angles. It also goes to 0 in the back-to-back two-jet limit. It has threshold at c equals 3/4 actually for four-jet final states where you can get non-planar events. I'm mainly going to talk about angularities, which were conceived by these authors some time ago now as a kind of generalization of thrust and jet broadening, and also contains the two in its class. So it's the sum over all final state hadrons of the energies times these A-dependent powers of the sines of the angles and 1 minus cosines of the angles to the 1 minus A, at least for massless final state particles. In that approximation, you can rewrite this sum as the sums of the transverse momenta weighted by this exponential damping factor of the pseudo-rapidity relative to the thrust axis. So take every particle's transverse momentum is then weighted by e to the minus eta times 1 minus A. And you can tune this A to be anything you want, at least A less than 2 for it to be infrared safe observable. In the limit A goes to 0, this is just the sums of the z momenta, that's the thrust, and in the A goes to 1 limit, this is just sums of the transverse momentum, that goes to broadening. But we can vary this all the way down to minus infinity if we want, over a continuous range, and I'll show you a handful of different tau A's in this talk. This form suggests that many event shapes can be written in a general form where you replace this function of the pseudo-rapidity by any arbitrary function that gives an infrared safe observable, at least for this form, at least for massless final state particles. And the C parameter can be written in that form as well. But when I vary this A coefficient, this A exponent in the angularities, what is happening intuitively? Well, if you look at the final predicted cross sections, the distributions, well, they look like this for different values of A. They become more peaked for small a, or large negative A, and more spread out for wide A. Kind of what's happening is if you pick a fixed point in this tau A space and ask, well, what do the events in the tau A distribution around that point look like for the A equals a half? At that point, you'll have very narrow jets in that distribution, and as you change the exponent A to smaller values, to lower values, the events get broader. Another way to look at that is in any of these distributions, if I kind of wanted to use tau A as a rough cut between 2 and 3 jet events, where does that appear relative to the peak of this distribution? For A equals to half, this peak is entirely dominated by things you would look at and call 2 jet events. As you reduce that angular exponent A, the three jet events move further into the peak. It contains, and then the very narrow 2 jet events get moved more and more towards the endpoint. So already you see here angularities can possess a very, their variable properties, various scalings, depending on the relative fraction of 2 and 3 jet events in the peak and the typical size of the jets that are in that peak. So when we try to predict and describe these distributions, we have to consider then several regions, which are common to all the tau 8 predictions. Because of the wide range of events you'll see across the spectrum, these event shapes, they probe QCD effects over a wide range of scales, much of them perturbative, but near the peak, there can be large non-perturbative. There are large non-perturbative corrections. The full predictions for these distributions will work out. Will take the form of a perturbative distribution. We'll convolve it with a non-perturbative shape function. So very near the peak, the distribution will depend heavily on the shape function. In the far tail of the distributions, where the events contain more multi-jet events, we can predict that in fixed order perturbation theory. But there's this interesting intermediate region where the non-perturbative effects you can show in an operator product expansion of the shape function. The dominant effect is just kind of a shift of the distribution to the right, which is parametrized by some non-perturbative parameter, which we'll find is universal for many of these event shapes, and it's nowadays usually called omega 1 order, which is an order lambda QCD non-perturbative parameter, and the shift is proportional to this amount. So we can control the non-perturbative shift, or we can parameterize the non-perturbative physics in terms of one parameter, and predict the distribution accurately in QCD perturbation theory as well, although in this region there will be large logs of the event shape and we'll have to use resummed perturbation theory. So a single event shape distribution contains information, depends on alpha S over a wide range of scales and even non-perturbative physics in the low tau and low event shape region. But because these, as I mentioned earlier, are global observables, very simple measures with a single number characterizing the entire event, in some sense they're easy to predict. Well, I'll say straight, now it's known now how to predict them to very high accuracy, relatively easy to measure. There are not that many cuts as in a cross-section with the JET algorithm. There's lots of data from LEP on a number of event shapes and other experiments. At least for tau, for thrust, C parameter, and heavy jet mass, there are resummed predictions up to the n cubed next to leading log accuracy for broadening N2LL. And what I'm reporting today in part is that predictions for angularities have also finally gotten up to the n squared leading log resummed level, matched to two-loop fixed order predictions. Very brief advertisement. There are event shapes in other collider environments like DIS and PP, which I don't have time to talk about in this talk, but they can be useful in those environments as well. So to advertise one of the organizers' work, very beautiful work, very impressive work. Well, of course, we're here to talk about many different ways to probe alpha S. And jet cross-sections and event shape cross-sections are responsible for some of the most precise determinations, especially in the Q equals MZ range where LEP had a ton of data. And a few of them are highlighted here from the PDG collection. A couple of these are these extractions here, which Vicente and his friends worked on a number of years ago. Showing the extraordinary precision to which you can determine alpha S and this non-perturbative shift parameter omega 1 from their n cubed leading log matched to three-loop fixed order predictions. So they come to these extremely precise determinations where we believe we understand a lot of the theoretical input into them. It's been noticed that these are a bit lower than the PDG world average. And so resolving this difference is one of the interesting problems to work on, think about in this field. And so that's one motivation to look at additional event shapes like the angularities as I'm talking about today. Just to delve deep, to advertise more of Vicente's beautiful work. So this is the theoretical prediction for the C parameter distribution, where this intermediate region where you have resummed perturbation theory being relevant and this non-perturbative shift being the dominant non-perturbative correction, fitting that region for those two parameters to the LEP data. This is what leads to that extraordinary precision, and then shows in the other regions outside the fit region, with those fitted parameters, the predictions agree with the data extremely well. I'm not sure have you ever I don't know if you knew that your plots in this paper can be pasted together I don't know if you know these plots from your paper can be pasted together like this in this beautiful way. So I just it's not, anyway, I just noticed that while making this slide, so. This shows the beautiful convergence from the lowest to the highest resummed accuracies, leading to this percent level prediction, both on the cross-section determination of alpha S. And then this nice illustration of the effects of the different theoretical improvements on the final value of alpha S that results. If you use a purely fixed order prediction, even up to 3 loops, but fit it to the data, you would get a fairly high value of alpha S. Adding in the resummed perturbation theory brings it down to this level, and then the next big effect is accounting for this non-perturbative power correction, this shift in that fit region. And then there are various other very impressive improvements which lead to smaller discrepancies. But in general, in these extractions, it seems that, yeah, these, especially this effect of accounting for the non-perturbative effect and doing a fit that includes that accounts for that, does lead to a lower value of alpha S than a purely perturbative fit. So I'm going to try to breeze through just an illustration of some of the theoretical ingredients that go into obtaining a prediction like this, and also for angularities, although not to the red precision, but at least to the blue precision. Using the tools of effective field theory, which is a more modern way to think about these problems in QCD, which has proven to be very powerful and has allowed that very high order resummation that I just illustrated. To identify and construct the right effective field theory, you need to know the physical scales in the problem, and the scales between which, the ratios of which give rise to those large logs in the perturbative expansions of these distributions. So I won't read the whole slide, but for thrust, if you measure a final state with a small value of the thrust, which is in this limit equivalent to the jet mass if you scale it by q squared, in these light cone coordinates with respect to the jet or the thrust axis, of course, you know that the jets, they're energetic particles in these jets, which have a large energy and then a small light cone component in the other light cone direction, and then an intermediate transverse component, which is forced by the measurement of the thrust to have the scaling of m from this relation, or q times the root tau relative to the thrust. But there can be soft radiation, there must be soft radiation exchanged between these jets. I mean, first of all, to exchange color and to lead to hadronization. But it's allowed that these jets emit soft radiation up to the value of the smallest collinear component, and that determines the scaling of the relevant soft radiation in this kind of final state. So q times tau in all components. Just as a contrast for broadening, where you measure the transverse momentum of the jets, particles in the jet, that measurement fixes the transverse component of the collinear and soft radiation to be the same instead of this light cone component as in this case. I'm only going to talk about the thrust-like case today. So for angularities, where I have this variable angular exponent, the measurement of a particular value of tau leads to an A-dependent scaling for the collinear particles constituting a jet that has that is measured to have angularity tau A. So the transverse component is fixed to have q times tau A to the 1 over 2 minus A. So for A equals 0, that reduces to the thrust case. And that's what determines the physical scale of the collinear modes. For the soft modes, I mean, even though there's A-dependence in the measurement of the observable, since all the components of momentum have the same scaling for soft, the soft scaling ends up having the same relation. The soft momentum is q times tau. But then there's this different relative scale relation between the collinear and soft scales. So this leads one to identify and construct the soft collinear effective theory to describe the degrees of freedom in these kinds of events. For thrust, also for C parameter, you have this theory, this cartoon, with this cartoon illustrated here, where hard modes are integrated out of QCD, matched onto a theory with collinear modes in the two back-to-back directions, and then the soft modes communicating between the two. For broadening, you would have all of them on the same, at the same virtuality, but that's a different theory. That's another version of SCET called SCET2 versus SCET1. So for the angularities, this collinear scale, as I just illustrated, has this A-dependent scaling, so you can move it further up or further down towards the soft as you change A lower or higher. We dubbed this kind of thing SCET1 plus A when we first wrote about this, but as long as the collinear is sufficiently separated from the soft, they're all basically SCET1 theories. So I'm just talking about SCET1 today. So SCT, this is your one slide lesson on SCT. It can be constructed as an expansion of the QCD. The SCET Lagrangian is an expansion of the QCD Lagrangian in the collinear and soft limits, matching quark fields and gluon fields in QCD onto collinear quark fields in SCT and collinear and soft gluon fields in SCT. I'll let you study this slide later. But conceptually, what happens is if you expand QCD around each of these these regions, you can show to leading power in the power expansion that the fields in the different collinear sectors are sufficiently separated. They decouple from one another. The soft fields decouple, in a sense, from all the collinear fields, at least after you sort of redefine the collinear fields with a factor of the soft Wilson line, this path-ordered exponential of soft gluons. You can write the Lagrangian in terms of these rotated fields in a way that the soft gluon sector, soft particle sector, is completely decoupled from the collinear gluon sector. So you can think of SCET for some multi-jet, to describe some multi-jet final states or cross-section, as a bunch of decoupled copies of QCD boosted in the different collinear directions, and then with a separated soft sector where the soft gluons don't interact directly with the collinear particles, but they're emitted from light-like color sources, which do know about the original directions and whether the hard parton initiating the jet was a quark or a gluon. But other than that, they don't know anything about the structure of substructure of the jets, and that sector decouples off completely. So that's just some words to describe some of the concepts and ingredients that go into SCET. And then one slide on how to use this to factorize an event-shaped cross-section. So when we predict an angularity or an event-shaped distribution at least for the two-jet limit, the prediction, if you do this matching of QCD onto SCET and then derive an expression for the cross-section, it factors in to a Born cross-section for the hard scattering process, and then a hard function, which accounts for integrating out all the hard virtual corrections to that process, which gives rise to a hard function that depends on the hard scale, and then a convolution of matrix elements of collinear operators in each of the different collinear directions in your process, and matrix elements of these soft Wilson lines, which account for all the soft radiation in the process. These factor from one another, but are then convolved in variables which describe each sector's contribution to the measurement of the final observable. So, just an example, if you compute these matching coefficients and matrix elements, get matrix elements to one loop in DIMREG, you get results that look like this. I just put this up here to illustrate how after this factorization, each of the functions, large logs of tau, which were in the original QCD expansion of the cross-section, separate into functions which have logs of the factorization scale mu divided by just the single physical scale on which that sector depends, which we identified just in those pictures earlier in the talk. So we can also use this factorized form once we know it, and each sector's dependence on this factorization scale mu, which must cancel out in the total cross-section, the physical cross-section. We can use those facts to derive evolution equations for each of these functions, use those evolution equations to resum the logs. And many of you are intimately familiar with this, so I'm not going to spend time on the details. I don't have time for the details. But each of the functions has their own evolution equations with anomalous dimensions, with a cusp piece that multiplies a log, and then a so-called non-cusp piece of the anomalous dimension, which is constant, has no log in it, which are subject to this consistency condition that they add up to 0 to give mu independence of the total cross-section. This cusp anomalous dimension in each piece is a universal thing. It's the same cusp appearing in all the pieces. You have to compute the non-cusp pieces separately, although this relation buys you one of them. And then you write the final cross-section in terms of, you can evaluate each of the individual hard jet and soft functions at a scale where the logs in them are small, and then use the evolution equations to evolve each of them to another scale where now the large logs between those two scales are resummed into these exponentiated forms. I'll skip this slide. Suffice it to say that to achieve a certain order of accuracy, then you need to compute these anomalous dimensions and then finite pieces of the hard jet and soft functions to sufficiently high order For the accuracy, we're going to go to, for the angularities and squared leading log accuracy, we need the cusp to 3 loops, the non-cusps to 2 loops, and strictly speaking, the constant pieces of the hard jet and soft functions to 1 loop. But we're going to use this, so this, you may have noticed I had a prime on my NNLL counting earlier. That means you evaluate the constant pieces to 1 higher order, which has some superior properties theoretically, but it's also better for matching onto fixed order predictions to the same number of n's that you have, to the same power of alpha as you are resumming the logs. Okay, so which of those ingredients were known for angularities and which did we have to compute? For the hard function, which is the same for all these two-jet event shapes I'm talking about, that was known to 3 loops. The cusp is known to 3 loops. And for the jet and soft functions relevant for thrust or C parameter, those were known to 2 loops, and then the jet even very recently, last year, to 3 loop, computed to 3 loops. But for non-zero A, when you change that exponent in the angularity away from 0, away from the thrust case, those were only known, the relevant jet and soft functions were only known to 1 loop, computed by myself and my collaborators some time ago. But that's all we had, so we could only go to NLL prime until last year. My collaborators independently of me have obtained the angularity soft function for arbitrary angularity now to 2 loops. And then we, in our work together, obtained the 2-loop jet anomalous dimension, non-cusp anomalous dimension to 2 loops from that consistency relation, and the 2-loop finite piece of the jet function by extraction from the program event 2. And also the matching onto the R2 is the matching onto the fixed order piece in the for large values of the event shape called R2, and we obtained that matching from event 2 as well. So that's just a slide to advertise the program that my collaborators Guido and Jim, together with Rudy Ron, wrote to compute basically arbitrary arbitrary soft functions for arbitrary measurements, almost arbitrary measurements numerically. I won't go through the details, but this program is what allowed us to get the 2-loop soft anomalous dimension, the A-dependent soft anomalous dimension, as well as the fixed order, the constant piece of the two-loop soft function. Just to show, I'm not going to read formulas to you. The non-cusp soft anomalous dimensions, depending on A, have that behavior. There's actually a nice analytic expression for integrals for those anomalous dimensions that are very easily evaluated, actually. And then the constant pieces, which do depend on their numerical program, showing the A-dependence of the 2-loop constants in the A-dependent soft function. But that's just to show that they're there. This is a very brief word on how we get the 2-loop jet function constant piece, which was still unknown. But now we have all the pieces that we need to be able to extract that information from the program event 2. So, which will give us numerically will give us the fixed order result for a QCD cross-section for basically any observable you can define in E plus E minus hadronic final states. The QCD prediction will have, this is what I'm calling the constant piece in the integrating cross-section, and then there's a non-singular remainder. We can extract both from event 2. So there's a trick required to get this constant piece, which we use the trick described by Huang and Kluth more than 10 years ago. I don't have time to really explain the details of that procedure, but the singular part of the distribution, this constant, sorry, I should use the same symbol, but this constant is the same as the coefficient of the delta function in the differential distribution. So how do you get a coefficient of the delta function from event 2? You get directly this non-singular piece away from tau equals 0. And then the trick basically boils down to the fact that although event 2 won't give you directly this coefficient of the delta function, you can, since it gives you this non-singular piece, you can get the total integral of the non-singular piece. And you already know the total hadronic cross-section, and that coefficient of the delta function has to make up the difference. So that's how we extract then what that singular constant piece is. And then we can get the QCD singular constant from event 2, and then we know how it depends on the sket individual constants for the hard and soft function, and then we can solve for the two-loop jet singular constant. So that's how we did that. Some pictures to illustrate the procedure. So one loop, I put we don't need to use event 2 for one loop, but just because the pictures are clean. So taking the difference of the analytic sket prediction for the singular pieces, taking the difference with the event 2 prediction for the full QCD cross-section, you get the remainder function in red, which is just the difference. It's non-singular, and the tau goes to zero limit. From that, you can try to integrate the whole thing and extract what is the value of the total integral of the remainder function, and then therefore extract the singular constant. That procedure works very well for the leading order, fixed order piece. At 2 loops, the next leading order, basically you do the same thing, although in the very small tau region, you start to run into issues with this infrared cutoff in event 2, so there's a limit to how far you can push this extraction of the singular constant. But hopefully, the hope is you can go far enough to extract what the value of the singular constant is. For 2 of the color structures at 2 loops, that still works very well, even for different values of the angularity. For this color structure, it's a little bit iffier. We can talk about that later over coffee if you want. Those don't affect the precision of our predictions at this level very much yet, anyway. But we extracted the singular constants and then the singular jet function constants. And the non-singular remainders, these are just pictures of the non-singular remainders. I don't need to dwell very much on this. They're there. But now we have all the perturbative ingredients we need to predict angularity distributions to next to leading log prime accuracy matched to 2-loop fixed order. So that's really all I wanted to say in that section. But before I show you final results, I have to talk to you about non-perturbative corrections very quickly. So in general, the full non-perturbative effects on the distribution, which come from the soft function in our factorization theorem, have to be described by some full shape function. And in the very small tau region, I need to know the whole shape function, so I don't really have predictive power at very low tau. But in this sort of intermediate region, I mentioned, you can show that the leading effect is a shift of the distribution away from the perturbative value to the right, parameterized by this quantity, which depends on a single non-perturbative matrix element of a so-called energy flow operator between Wilson lines. And that parameter, although in principle, when you start this derivation, it appears that this omega 1 depends on which observable you're measuring, like thrust or C parameter or angularities. But you can show that actually it doesn't. And the total non-perturbative correction scales like that universal matrix element times 1 over Q, and for angularities, times 1 over 1 minus A. There's some other technicalities that I don't have time to go through at the moment. So the scaling times this universal parameter, it's a prediction of factorization in QCD, whether you derive it using SCT or in pure QCD. That's a prediction of the factorization at leading power. So this scaling is something we are hoping to exploit. I mean, when you do these fits, I showed you these ellipses in this 2-parameter plane, and there's a degeneracy between alpha S and omega 1 when you fit the data. So Vicena and friends already used the 1 over Q scaling, however, to break a lot of that degeneracy by comparing data from many different values of Q measured at lab. But for different event shapes, particularly for angularities, there's this additional scaling of 1 over 1 minus A. So now we can also think about changing this A to break this degeneracy. Just numerically changing A within this range is numerically equivalent to varying Q by a factor of 6. Although for different A's, you're using the same experiment, so there's more correlation. But ideally, you want to see, as you vary A, when you fit these 2 parameters, alpha S and omega 1, that when you overlap the ellipses, they break the degeneracy that's in any single one, leading to a more precise determination of the 2 parameters. There's original proof of that universality of that shift, which at least worked for the massless final state case. descent fixed it for massive final states. That's in the backup slides. You can look it up later. But the final form of the theoretical predictions, just ignore the bottom part of this slide, is the perturbative part of the distribution, the resummed singular logs, this singular logs resummed into this piece, matched onto the fixed order tail in this piece, convolved with not the nonperturbative shape function, where this is to illustrate we implemented renormal on subtraction, so I didn't have time to talk about. But based on that result, then, based on that prediction, I can show you what the cross sections then look like. Before I show you the cross sections, to explain what the uncertainty bands, how they're determined. So in this factorization, factorized and resummed form of the cross section, they said you can evolve these soft, jet, and hard functions from different scales to the common factorization scale. So all of those are varied around some central values. This also illustrates that those scales, as a function of tau, can be chosen so that they reflect the physics that's going on in the problem. So in the very far tail region, you don't need resummation. So the scales are designed to merge into a single scale in the large tau A region. And in the intermediate region, they reflect this hierarchy of scales that exists between the soft, jet, and hard sectors, evolution between which achieves the resummation of the logs. So this, to compute the uncertainties, we vary. We randomly scanned over the parameters in these scale functions, these scale profile functions, to get some uncertainty estimate. The resulting envelope for our predictions these are the integrated distributions for angularities, showing a very nice precision at the highest order and a very nice convergence from one order to the next. And this is zooming in on the differential distributions to show off the beautiful convergence of these predictions. And there's data on these from LEP. For the L3 collaboration, reanalyzed LEP data in 2011 to give us results in angularities. So this slide, it's not yet a fit, but we just plugged in values of alpha S and omega 1, which are roughly consistent with what came from those earlier thrust and C parameter determinations, and showed, oh, look, they agree with our predictions, the red boxes, which include the non-perturbative shift and the highest order resummation we have. And that agrees better with the data than the purely perturbative predictions, at least for these values. So then, well, we said, well, what if we plug in the PDG world average for alpha S? And then we tuned omega 1 by hand so that the prediction fits the data well for the large value of A. But then for those values, then the prediction doesn't match the red prediction, including non-perturbative shift for small values of A. You could have done the exercise the opposite way as well, just showing visually, okay, well, it seems like these values fit the whole range of data better than plugging in the PDG value. So finally, in the negative time I have left, I'll show you our recent work. So now we are working on doing an actual fit of alpha S and omega 1 using the angularity predictions and data. We wish we had more data, but I'll show you what we got. I'm not going to call what I'm going to show you results yet. I'm going to call them preliminary exercises, because so you can't quote any numbers I show you. But because there are some important caveats in what I have available to present to you right now. So we have to treat correlations of uncertainties correctly. And the fits that I show you today you don't actually use the theory predictions convolved with a shape function, but that just shift over the distribution, just because that's faster to run in our code. We haven't had time to run the fully convolved theory predictions for our fit yet. Anyway, so given that, and the fit windows are where we fit in a region where we think that the resummed perturbation theory is relevant, and the dominant non-perturbative shift can be parameterized by this universal single parameter. So first, exercise, just pretending we can fit all the angularities simultaneously, just ignoring that they're actually correlated, but just seeing what we got. this is fitting the available lab data to our predictions for all the angularities between -1 and 0.5 that for 7 different values of angularities in that range that they gave us. And the initial exercise just yields this fit with this uncertainty range, which comes out with a central value that is consistent with the results from the thrust and C parameter extractions, at least comparing to their results, just stopped at the same order of accuracy that we actually have. So that's interesting. That's very preliminary. So if you take this apart and try to fit the angularities each individually, so this is what we get so far. So for A equals -1, the fit is up here at a pretty low value of alpha s. Now the best fit value of alpha s does go up, and the omega-1 best fit goes down for higher values of A. But there is this degeneracy, right, between them again. If I overlap these ellipses, which I didn't do for this slide, they would overlap in a region that's consistent with the number I showed you on the previous slide. So I better stop. There are many questions you can ask that might be addressed in the backup slides. But we do have now angularities predicted to this accuracy. We have preliminary fitting illustrations, but still a lot of work to do before I can show you what I would call the result. But I think our studies so far encourage us, at least, that there is value in examining multiple different angularities for this fit. But they also show us the importance. I mean, it would be great if we had additional data, either from people who have past archived LEP data or looking forward to a future collider. So I better stop and let you ask questions. So, thank you.
So we are a little late, but we have time for 1 or 2 short questions, or yes or no questions.
So I just was wondering, I mean, to what extent or how sure you are that all these non-perturbative effects can be parameterized by one single parameter? What if you need 2?
So yes, in principle, you need this whole
I mean, even
shape
if it's
function.
a small correction, right? I mean, I can see that.
Yeah, there's so I mean, yeah, theoretically, I mean, you can derive that in this, if you're sufficiently far away from this limit, or that's not the cross section, but you can, there's a hierarchy in this, you can show in the power counting that the higher sort of moments of the shape function are suppressed by additional powers of 1 over q times the value of tau you're looking at. I mean, Fizet and friends, in their thrust and C parameter fit, they did include, believe that the first moment is the dominant correction. I think you included the second moment as well in the fit as a test of its robustness.
There is a limit. Once you fix the value of omega-1, omega-2 can only vary within a range. So you put this omega-2 and vary within the range, and essentially nothing is happening.
Yeah, but
it's pretty much very less.
But I mean, it's a small effect, right? But I mean, you have huge ellipses. Now you add a third parameter. I mean, it will become more. So how sure you are that it will be
I guess we need Vicent to give a talk and show the plots from his paper that show the dependence on including the second moment. But
question.
A very short, fast question. This omega-1 is pure lambda QCD. Does it have a Wilson coefficient or anomalous dimension?
It does. So this is the very simple version. Did I include a backup with enough information to address your question? Maybe. I don't think I meant, but it does have an anomalous dimension. This is a version that includes hadron mass corrections that Vicent and friends worked out. Yeah, if it does have a matching coefficient and an anomalous dimension, but they're in Vicent's paper up there. So we can look at it later. Yeah.
Thanks. Let's
Right.
thank the speaker again. And